Yeah, hi, my name's Brian Brown, and I'm putting together some introductory math courses and statistics for students taking beginning economics and business economics. I will upload these lectures to my website, which will be h2oecon.com/math.html. A sequence. We're going to talk about sequences, geometric sequences in particular. A sequence is a set of things that are in order, normally numbers, or usually numbers. Here you see a sequence 3, 4, 11, 15, and 19. And it doesn't take too much looking to see that it's 3 plus 4 is 7, plus 4 is 11, plus 15, plus 4 is 15, plus 4 is 19. And of course you could say 3 plus 4 is 7, 3 plus 8 is 11, 3 plus 12 is 15, and so forth. So two ways of looking at a sequence. A geometric sequence. A geometric sequence is where the previous number is multiplied by a constant, also known as a common ratio. And this may be shown as a simple algebraic presentation, where a is the first term, whatever you set it, here 3. R is what we call the common ratio, and it gets raised to a power. That's the geometric progression that we've been talking about. So a is the first term, AR equals the second term, AR raised to the second power. This just means raised to the second power, and third power, and so on. So if you just, now each of these are elements in the sequence, separated by a comma. But you may want to sum them up. You may, instead of saying the comma, you may want to say A plus AR plus AR raised to the second power, and so forth. And we're going to talk about a formula to do that. And we're also going to talk about how to figure out, if you want to look at a sequence where you have an equation for it, how do you find the nth? And the nth could be any number, so any subjective number you define. So here we take a look at 3, 6, 12, 24, 48. There's two ways of looking at it. A, of course, is 3, and AR is 3 times 2, because 2 is only raised to the first power. The next one is 3 times 2 to 2, raised to the second power. 3 times 2 times 2 times 2 is 8, times 3 is 24, and you can see that up there. And it goes on. The sequence has a common ratio, or constant ratio of 2 between each number. This sequence could be written this way, and I just happen to move this equation up here and didn't think to take that out. Okay, the nth term. The nth term is sort of like a placeholder, arbitrarily. If I say n equals 5, then just say 1, 2, 3, that's the fifth term. And here you can guess what the common ratio is. 10 times 3. And then you say 10 times 3 squared. Well, 3 times 3 is 9. 9 times 10 is 90. Or you could just multiply 30 by 3, gives you 90. And you can just go, you can take each element and multiply it by the common ratio as you progress up, or you can do it in a more geometric format like this. 10 times r to the 3. That's not right, so that's a good one. We picked that. It should be 10 times r to what? 1. 3. And if we did do 10 times r to the 3, it would be 3 times 3 equals 270. I actually corrected that below. Adding these 3 lines means continued. Open-ended means continued to infinity. And this is the infinity symbol. We all know that to be like an 8 lying on its side. How does one find in a geometric progression the value of the nth term? Well, it's fairly simple. Because the first term isn't operated on, you go, say you want to look at x to the 4, then you go AR to the 4 minus 1. Or so the general way of writing that is AR to the n minus 1. And let's see if I can do that there. AR and then n minus 1. So that's fairly simple to understand because it's not, the first term isn't operated. First term was there. It wasn't created by any geometric progression. Or it could have been, but we didn't start with that. Now let's look at a line is one-dimensional. That's R. It's got a length. A two-dimensional object is the square. So that's R2. A three-dimensional object, R3 is three-dimensional and is a cube. And there's a cube. Here we've got a picture. And so on. We can have greater than 3 or more than 3 dimensions in mathematics. I'm just alerting you to that. Now, summing of a geometric progression. Sum is represented by the sigma sign often. Here's a sigma sign, or sum. You've seen the Greek sign. Anyone who's looked at, has Excel as a program can raise it, and you can see. Well, can I get it down here? Yes, I can. There, if you've got, say, three numbers, 10, where's this? 10, 21, and 15. So you just conveniently go over, you scroll down like that, hit the sigma number, and you get an answer, 46. So I think you're all familiar with what sigma stands for. Worth just chatting about it. Now, if I was going to write a simple program in QBasic, and I recommend that anyone taking beginning economics does study QBasic. It's an old program, one of the very first computer programs, and I don't think you even find it readily today. I found it online and I downloaded it, and of course I grew up with that and Fortran and some other programs that no longer used. But let's say I had I have read in 10 data points. So that would just be read for A equals I to 1, read such and such. They could be people's ages, heights, anything. But I want to sum them all. So I say for I equals 1 to 10, sum equals sum plus AI next. So every time it sees that this command here states that as the first AI, it could be, let's say it's weight, 200 pounds. So it reads A1, and that's 200 pounds, and it adds it to this variable here called sum. And then the next one, it could be the second weight, could be 150, and it goes, and it'll say plus 150, and it'll add it to the 200. It goes through until it adds all 10. And the next 10, it goes on to, when it gets I equals 10, it goes on to the next routine. But then I say print sum, and if you get QBasic or some simple program, Fortran, or some of the, or Java, you can do it with any of these programs. And I have done that, but I still find that this is so easy and it's a good teaching tool. So now I set up an equation because we talked about a sequence, but we want to know what the numbers in the sequence sum to. Now, they might not be as easy as this. So the equation is for n equals 1 to 4, that's from the first element in the sequence to the fourth sequence, or it could be the 10th or 20th, or whatever you want to define this. N is 1, and this could n is 4 in this case. So you mean sum from element 1 to 4, and k is the counter. And that's just what I was doing here, counting. And so here's the equation. It's just sum AR raised to the k. That makes sense, right? And you go through N1, and you just sum all this, not much different than what I did here. But you can simplify the equation by saying A, which is the first term outside of 1 minus R raised to the N. In this case, it would be 4. In this case, up here, where I don't have another one there, do I know? Here it would be, and I might want to add all these. It would be 1, 2, 3, 4, 5, N would be 6, whatever you want to do. And so it's 1 minus R to the N, raised to the N power over 1 minus R. And you should do that example. Well, here, I've done it down here. 1 minus 81, R to the N minus 1 over 1 minus 3, and it comes out to be 400. And I have that on an Excel sheet, which I'll add up. And here's where I've taken one of my Excel sheets and pasted them into PowerPoint. And A is equal to 10, and R is equal to 3. Sorry that you can't see that here. I've specified the steps 1 through 6, and then I've specified the first data read in is A. The second data point read in the sequence is A times R. The third is A times R to the second, A times R to the 3, A times R to the 4, and A times R to the 5. And as I said, A start with 10, but here you can see you've got the sequencing. R is 3, R raised to the second is 9, 3 is 9, R raised to the third, remember, is 27. But remember that while we're raising it to the third, it's the fourth number or element in the sequence. That's why in the previous example, where if I said you want to find n, you want to know what n is and use your equation, it's n minus 1. And here we come down 5 and so forth. And here you start with 10 and you get 30. This is what this produces. These are the values produced by A times R squared, and so forth. But then I sum them over here, and you can see you've already got 10, you've got 30, so 10 plus 30 is 40, and you add that on to 90, 130. There's your 400 that we calculate, and so forth. It really is worthwhile for you to sit down with a pencil and paper and go through these exercises. I mean, they seem fairly simple, and they are, and they seem very intuitive, but you need to work through them so you become familiar with them. But this has a lot of relevance in economics, especially when you get to capital theory and you're trying to work out present values of a series of elements in a sequence. I'll go to the next one. Another problem of this one I think you should do. I did work through this, and I got the book that I was getting this from. It had a different answer than the one I got using the formula in BASIC, and slightly different to the one using Excel. But they were so close that it just was a machine error. But I got interested in this as a young man, young boy, 10 years of age. I had a horse. And I went to the blacksmith and I said, how much to shoe my horse? He said, well, 25 cents for the first nail. The next nail will be 50 cents. The next nail will be $1, and so forth. I will keep doubling it. Did I get that right? 25, yeah, double 50, $1, and so forth. So that was a geometric progression, if ever I heard of one. And you should do that for a horse. There are approximately, I think, 8 nails per shoe. There's 4 shoes, 32. So have a crack at that one. You'll be surprised how much a shoe can cost if you take that start with 25 cent steel. Another good one is a chessboard with 64 squares on it. If you put 1 grain of salt on the first square, 2 on the second, through 64, how many grains of salt do you utilize? So if you use Excel, you can use Excel to do that. You can use your calculator. You can write a quick program, or you can just work it out with the equation. And here I didn't do all the things, but here is and I did it at 1, that's 1 grain, and it increased by 2. And if you look here, I started the various steps. The first step, and is, remember, 1, 2, 3, and at the 64th step, or I feel it's, what is this, 18 trillion or something? I'll let you figure that out. But I did it all 3 ways, and I will put up some basic programs. I think they're neat, and I strongly recommend you try them. Kids used to love doing basic programs. Grade school kids and high school kids back in the old days, I don't know, they probably got so much sophistication today they're not necessary. Okay, so look how quick this solution is using a simple basic program. Well, here, these are the actual steps. A equals 1, I just said A equals 1. R equals 2, N equals 64. I just gave them values. The computer knew that. And I wrote the word sum equals A times this, and print sum, and it printed out the answer. That's how quick that long, once you use the equation. I'm going to leave that for you to do. I don't think that could be any simpler. Just remember that you have to take the inner parens away first if you want to do it by a hand. And that then you do this step where you divide this numerator by this denominator, then you subtract from 1, and then you multiply by A. It's very important that you realize how the computers do the steps, the inner parens first, and they work outwards. I got that down there. Anyway, so what if n goes to infinity? Well, this is a very interesting step, a very interesting concept. The British, at one point in their history, took all their debt and put it into what they call British consols, which paid a certain fixed amount every year. So you could buy a console for £5, and since I don't have a pound symbol, well, I do, but why confuse the issue? So if you buy a right to receive £10 or $10 each year forever, how valuable is that for it? How valuable is that annuity that you've just purchased? Well, you could do simple calculations where you could just go, the first year would be 10, well, you're done with it. The first year would be 10 / 1 plus, and say your discount rate was 5%, so there'd be 0.05. Where's my 5 here? Here it is. And what? That's no. 05 raised to the first power, right? You do that to see what it was worth in a year from now, what $10 was worth a year from now. If your discount rate was 5%, if it was 10%, you change that to 0.01, and so forth. But you'd take that out forever. Well, that would take you a long time to do, and you'd sum that to the next one, which would be 10 slash 1 plus point, well, I changed it to 10%, so slash 2. And again, you have to be careful how you pull the parens out if you were doing this in any form of any rigorous way. You do it this way. So it would, and you see, every time the future value of the dollar would go down, try this with your calculator. So it would be about $9, a year from now, it'd be 8 something in 2 years, and so forth. And then you'd sum all these amounts way out to infinity, out to here, and that would tell you how much the present value of that $10 annuity going on forever is. Or a short way, or a quick way to do it, and we'll come to this is why it's important, would be just to write 10 and put it over 10%. This is for a perpetuity ad infinitum annuity, and that would come out to $100. Do that calculation, and if your planning discount rate was 0.1, 10%, then buying in that you would pay or sell, if you had it, one would be a demand to hold, and the other would be a demand to buy. If it was at this rate, you'd be willing to pay $100. And you can see if the discount rate is less, if the discount rate goes to 5%, 0.05, then the present value using this formula goes to 200. So I'd leave that in there for you. So here is the, we'll go back here. I just want to step ahead because I'm trying to relate what we're doing with sequences to economics as well. And capital theory is one of the most important fields in economics. Not that I believe economics should be broken up into fields, but it's one of the most important studies. So here is the formula which we've done before, and you could work this out. And here I've given, I've written down the, well, don't count this, I'll take this out now. This is a simple step using BASIC to show you how you could put this equation into a basic program. All right, let's continue on to the next step. Now, let's take a look at the sum equation. So the sum, S or sigma. So we know the sum of a sequence is A plus AR plus AR to the second power and so forth, all the way out. And then if we multiply S by R, we get this expression. And if we subtract that expression from the original expression, we finish up with S minus R equals all these equals, what have I got? S minus R equals A minus ARN. S minus AR. Yeah, I got it right. And then if we rearrange our terms, we get S outside of 1 plus 1, S is 1, and the S in that is R. 1 minus R equals A, put A outside, is 1 minus R to the N. Then if we make this, cross this, or make it the denominator on this side of the equation, we get this, and if we cancel out, which is our equation, we get A outside of 1 minus R to the N over 1 minus R, which is what we had earlier. But we actually, I just told you this equation earlier. I never derived it. Now I've derived it from this algebraic expression. Now I'll leave that up there for a minute. And well, first of all, I'm going to upload this. So I think you should take this, look at the PowerPoint and correlate it with the discussion we've had. This is very important in first of all, taking the present value type thing. So now we'll go down to the next slide. Let's go to infinity. Now, infinity is one of those concepts we all have trouble with and we all wrestle with, but And it came up many centuries ago. Zeno, the great Greek mathematician, and he basically predated the modern fast camera, where he said, if you fire an arrow, say the length between the archer and the target, or if you run between or whatever, there every there's an instant when that arrow is stationary. Take a picture of it. It's stationary. And so it has to go through infinite number of steps to go to the next point. And this is one of these paradoxes. So how does that explain that you've got to go through infinite steps, and you've got a runner racing a tortoise, and the tortoise gets to start? Can the runner ever catch you? Well, not if he has to do infinite number of things. So that was resolved mathematically, and I'll leave that to you. A great book that I recommend that anyone that wants to get an interest in math is this book, Mathematical Principles, Theories, and Things. And I'm trying to look at the stuff. And by the way, when we talk about infinity, I'm trying to think of the guy's name. I can't see it here, but there are not an infinite number of divisible. You cannot infinitely divide light waves. There is a limit. In other words, they don't go to infinity. They go to a limit, a small amount of value. And that, if you study quantum mechanics, you'll get a better feel for that. And so let's change the series to a half, a quarter. What are we doing here? A is a half, and we're multiplying it, and R is a half, and we're just multiplying it all the way out. This is no different. Remember, the numerator is on top, the denominator is on the bottom. Just do this. So if we go from, here's a sigma, AR raised to K, and we go through, start at 0, and we go through infinity, we develop this type of equation. And that equals a half over 1 minus 1 minus a half equals a half times 1 over half, and that cancels out to 1. So this is just the solution to the fact that you can go from 0.99999, there is a 1, and that's worth studying this equation and understanding how that was arrived at when you go to infinity. Adding a half plus a quarter plus an 8 equals exactly 1. I mean, if you keep going out to infinity, I just didn't. Where's the infinite sign? I don't see it. Here it is. Correct that now. Edit. Copy. Okay. Note, the action takes place with the denominator. That's on the bottom, not the numerator, top. So if you cross multiply, you come to 1. And that is more, and I'm trying to think of that guy's name. Maybe I got it written down somewhere. But now infinitely continued. Does 0.999 mean 1? Remember Zeno's paradoxes, well, we just discussed them. Then we can't, here's a guy, Max Planck, who showed that energy light is not divisible infinitely. So we don't have to worry about that in this course, but we have to know that there are some things in nature that you just can't go for infinite series, like taking 1/millionth and then 1/10 million and never reach a 1. So here we have taken this example, and we're proving it to be 1. We've just substituted it into our equation, 0.9. 1 minus 0.01 equals 0.9, and if you factor out, you get 1. Yes, 1 does equal, 0.999 does equal 1, and I think that's not too difficult to see. You can see this crosses out with this, and it leaves 1. So work that equation a few times, and or if you've taken the course from me, email me, and we can discuss it. And I will present a slideshow with just this as a topic, but I'm trying to get you introduced into geometric regressions. Oh, and here's how I showed how if you use the spreadsheet, you can asymptotically approach the 1 here. Look, 99999. Well, if you use the equation and as we did, it cancels out and becomes 1 at that level. Now we're talking about perpetual versus long series, capitalization versus present value calculation. How much is a perpetual annuity of $10 worth? Well, we already discussed that. It depends on your discount rate. Remember, if you have a 5% discount rate, you divide 10, if you want to know what it is forever, you divide 10 by 0.05. Remember, 0.05 is 5%. We normally write a 5 with the percent sign. This depends on the subjective discount rates. If your subjective discount rate is 5% or 5%, how would you evaluate a perpetual annuity? Well, here I've done that. And using the geometric formula for perpetual annuity, we come out with the same result. 10, that's A, 1 over 1 minus 0.05, that crosses out to be $200. That just proves what I was trying to say. When I first took capital theory, a professor put that simple equation on the board of the numerator being the annuity and the denominator being the discount rate, but he never proved it. So when I saw this, I thought, this is refreshing. I'll present this to the students. There is a proof, and there's also a proof of our equations that they're accurate. Well, I think that's enough for now. I want to thank you all for listening, and I hope this makes sense. You're going through it a number of times. I kept changing it. So this is a first effort, but I have to start somewhere. Take care. Bye.